In this video, we're going to be talking about the fundamental accounting principle. The definition of the fundamental accounting principle, or FCP for short, which we're probably just going to call it that because it's a very long name. For FCP, it states that you can find the total number of outcomes for two or more experiments by multiplying the number of outcomes for each separate experiment. So we're going to be multiplying a lot here. You can also use a tree diagram to illustrate possible arrangements of objects, which is going to give you the same outcome, they're just a little bit more time consuming. So in this first example, it says Antonio rolls a 1 to 6 number cube and then flips a coin. How many outcomes are possible? So this doesn't say anything about probability, so we're not going to be thinking in terms of fractions here, so that's what kind of the one thing we need to separate here. When we talk about FCP, it's just going to say how many outcomes are possible. So on this dice, when you roll a die, you will have 6 possible outcomes. You could roll a 1, a 2, a 3, a 4, a 5, or a 6. So that's 6 possible outcomes on the die. And when you flip a coin, you can either get heads or you can get tails. That's only 2 possible outcomes. So FCP states that when you're finding the total number of outcomes for 2 or more experiments, you're going to multiply the number for each separate. So rolling the dice, 6 times flipping the coin, 2. 6 times 2 is 12. So that means there are 12 possible outcomes. A possible outcome, if you're still confused, could be Antonio rolls a 1 and then maybe he gets a heads. So that's one of our possible things. Another outcome he could get with a 1 is getting a tails. So then you would have a 2 and a heads, a 2 and a tails, and so on. So that's how we get those 12 possible pairs there. Looking down at the next example, it says Sarah picks a colored block from a bucket. There are 5 colors: red, yellow, green, purple, and blue. She then replaces the block and chooses a second block. How many outcomes are in the sample space? So reaching into her bucket with these 5 blocks, she could pull out any of these 5. So on that first pull, she could pull out 5 different colors. Then she's going to put it back, and there's still 5 different possible colors for that second pull. So again, there's 5 outcomes. Multiplying these 2 separate experiments together from pick 1 and pick 2, she has 25 possible outcomes here. 5 times 5 gets us 25. And an example of that could be she could get a red and then she could get a blue. Or she could get a red and a yellow, a red and a red and a green, a red and a purple. So you can see that we're going to have many possible combinations here, and that possible number is 25. So let's practice these. If you want to pause the video and try them on your own first, feel free. I'm just going to go through them here. In number 1, it says Kirsten owns a black pair and a blue pair of jeans. She has red, green, and yellow shirts. How many possible outcomes could she make with these items? So we're first going to look at possible pants and then possible shirts, because when you make an outfit, you need one of each. For her pants, she has 2 pairs of jeans, 1 black and 1 blue, so that's 2 possible outcomes. For her shirt, she has a red, a green, and a yellow. That's 3 possible shirts. So we're going to multiply her pants by her shirts, so 2 times 3 gets us 6 possible outfits here, or outcomes. And that's what we have. In number 2, it says how many possible outcomes for a 3-character password would there be if you take a letter from the word math, a digit from the number 145, and a symbol from $sign or $sign. So we're trying to make a 3-digit password here. So there's 3 blanks that we need to fill. The first blank is going to have the option of being an M, an A, a T, or an H. So there's 4 possible outcomes here because it wants to be M, A, T, or H. Then the second one is going to be a 1, a 4, or a 5. So there's 3 possible outcomes there. And the last one, you can either have a $sign or a $sign. So that's only 2 possible outcomes with that. We multiply all of our possible outcomes from the separate spaces, and we get 4 times 3, and that's 12. And then 12 times 2 gets us 24 total possible passwords here. Looking at 3 and 4. So number 3, you're going to have a little bit more space to do this tree diagram. So let's try that on a separate page. We have an ice cream shop that is selling 2 different serving sizes. There's small and large, we could say. So we have 2 sizes, and I'm going to call those small and large, S and L for short. And then we have 5 flavors here. So maybe the 5 flavors are going to be vanilla, chocolate, a mint, a berry, and like cookie dough. And then it says we have 4 different toppings. So possible toppings for an ice cream sundae, maybe we have some sprinkles, some whipped cream, a cherry, and some fudge. So to make the tree diagram, you want to start with your first possibility. So the person's either going to choose a small or a large. Once you decide on a small, you have to decide on which flavor am I going to get. So in each flavor, or from the small, we could either choose vanilla, we could choose chocolate, mint, berry, or cookie dough. If you want a large, you could get all those same flavors. So we're going to say a vanilla, a chocolate, a mint, berry, or cookie dough. So already we have 10 possibilities here, because we could have a small vanilla, a small chocolate, a small mint, small berry, small cookie dough, and then a large in all of those flavors. So that's already 10 possibilities. Then, say you want a small vanilla, you have 4 other possible toppings to choose from. You have sprinkles, whipped cream, cherries, and fudge. And if you choose chocolate, you get those 4 options as well. So this is where you kind of have to start squeezing your handwriting in. It is a little hard to do. Do your best to write it neatly. You get these options on every single flavor offered by this ice cream shop. So go ahead and finish filling in your tree diagram for the remainder of the large flavors now. So once you've filled all those in, your tree diagram should look something like this. And this is just kind of proof that the fundamental counting principle works. If you would go through and count every single part where we have sprinkles, whipped cream, cherry, fudge, we have that all through this entire thing. If you went through and counted every single one of these possible options, because this is a sprinkle with vanilla with a small, a whipped cream with a vanilla with a small, there's going to end up being 40 different options there. And to prove that that's our fundamental counting principle, we take our 2 sizes, multiplied by our 5 flavors, multiplied by the 4 toppings. 2 times 5 is 10, and 10 times 4 is 40. So there's 40 possible sundaes here at this ice cream shop. So you can see the tree diagram's a little bit more elaborate. You do need to know how to make it, but when we have these in our practice problems and on our test, it won't be quite as long and time consuming there, but do make sure that you're writing these carefully and not forgetting like one of the flavors or whatever it is, okay? Now we already did number 3 together. For number 4, how many different outcomes could you have if you had the following options for breakfast? So no tree diagram here, we're just going to use FCP again. So you have the choice of scrambled, sunny side up, or poached eggs. So that's 3 different types of eggs. And then you have the choice of bacon or sausage. So that's 2 different types of meat. And then you can choose milk, orange juice, or apple juice. So for your drink, you only have 3 choices there. So 3 times 2 is 6, and 6 times 3 is 18. So there's 18 possible breakfast outcomes there at this restaurant, or maybe mom's being nice and giving you all these options. So you have these different choices to choose from. So that's your fundamental counting principle. Just remember, you're going to be multiplying the possible outcomes. We're not dealing with probability here. It just wants the number of outcomes. So you should be in the whole numbers here, no fractions needed. Thanks for watching.